First video we actually do logarithm decrement. Okay, the two videos. So this video will talk about chapter 4 force vibration, and this video will mainly focus on the concept and definition of the force vibration. And then the next video will derive how to actually predict an equation to actually solve the problem. Okay, force vibration actually will have a problem, so I'll just talk to you about it. So imagine you have a damping system, okay, and then this is a mass, some material, and then you attach a chop, okay, you attach a chop. Normally you want to chop something, right? So maybe this is like Singapore. Then you want to chop onto the mill. There's a mailbox over here. You want to chop. So imagine you want to create a chopping system, a automatic chopping system. Okay, so imagine, so you start to this thing will start to go down, and then you chop, and then the next item will change. So this one will go up. So another next item will come in again, and then you chop again, chop, and then so go in, and then I think you get what I mean. So but however for this, because in order to have this chop, so how do I say? So the time required for this to reach here has to be equal to the time to change the one item to another item. Okay, because let's say at time 1 you chop this thing, and at time 2 it comes back over here. Okay, by time 3 you would expect that it will come down again. Okay, correct. So by time 3 the item should be gone already. By time 3 then the next item should be here, okay, instead of the previous item. So you want to set a timing that corresponds to another machine that actually change the item, which is another timing. So in order to do that, you have to make sure this system is stable. It is always the first second come down, the second comes up, the third second come down, the fourth second come up. So you want it to be constant. And how do you do it? Okay, so apparently there will be a force trying to pull this mass down, and then so this is a forcing function relative to the mass itself. The mass, relative to free vibration and then free vibration, their forces are some whatever forces that does not um continue to let it move. There will not be any constant forces acting on it. So as you can see, as I say earlier, this force is constantly um bringing this whole thing down one by one, like time by time, maybe 1 second by 1 second, 1 second by 1 second, 1 second by 1 second. So in other words, force vibration is like a moving, it's like a move. The force itself causes the whole system to keep moving and moving and moving and moving. Okay, whereas free vibration, you just pull the mass down and you release, you let it decay down, and that's it. Okay, so the difference between free and force vibration is this thing. Free vibration, you pull the mass down, you release it in them. But however, for force vibration, you keep pulling it down and up, and then release, down and release, down and release, down and release. Or maybe, yeah, correct. So I hope this makes ample sense. And therefore, how do we achieve the timing, okay, such that it's constant, okay, time 1, time 2, time 3, time 4, okay. So time is actually the time, okay, you know what I mean, time. So at time 1 second it goes down, time 2 second it goes up, time 3 second it comes down. Hope you get what I mean. So yeah, okay. So what is the problem actually? The problem is to actually, because when the very first part, when the very first time you pull the mass down, you require a larger, not larger force, but rather how do I say it? A amount of, you require more time in order to to pull this down, okay, compared to when it is constant, because you pull it down, you have to resist. There is the spring constant and the damping, the damper itself to actually resist the forces over here. So when the very first time when you pull, you have to you have the damper and the spring constant to release. Then when you release the second time you pull again, you have to you the amount of the distance you move can be faster. Okay, so at first the first time you actually pull it like that. Second time you release and then you like that, then like that, and then you start to dun 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 dun. You know what I mean? So I can't explain in good words, but so at first you need to overcome certain um the static somewhat analogy to static friction lah. Okay, so you have to so the very first time when you pull, you have to slowly pull, and then when you have certain momentum already, you start to comes in. So the momentum itself is, as if you remember, is mass times initially, okay, momentum is p equals to mass times velocity. So initially the velocity may actually be very slow, right? Because you want to pull this down the first time. Then eventually when the velocity start to increase, the momentum start to go up. So you can say that these points, okay, these are the when this is actually the x position, okay? This is the distance x, if you remember. I mean, sorry, if you, let's say your new position is here, maybe I should use my pen. Okay, so imagine you have, this is the thing. So this is the distance x move, okay? And then this position, okay, this position is x, the amplitude, okay? X and this x, if you remember, this x is the distance move. This x, okay, is the amplitude, okay, the position. So we are recording the position in accordance to time. Okay, I hope this was pretty much clear. And therefore, as I said earlier, the velocity would, you have to, in order to have a constant momentum, like so this is the constant momentum where the velocity, yeah, I think you get what I mean. So in order to reach this momentum, the velocity has to increase, right? So the amount of force, so eventually I think you get what I mean already. I don't need to complicate you much, because I myself is also don't know what the hell. But so at the very first time, uh, you may actually require more time to actually console, and as the system goes, as time passes by, this one will start to go faster and faster. Okay, so therefore with this concept, in order to to set this as one, time two, time three, time four, as so in order to let this oscillation be constant, okay, which is this one, okay, then it's always constant, the amplitude, and it's always constant. In order to let this happen, okay, you need a certain setup time. So this portion is the setup time. So within this portion, you don't have any item. You don't put any item over here to chop. Okay, because the time itself, you can't control that that significantly. So when it is constant, um then you can start to bring in the item and you chop. But as a businessman, you want it to chop faster, right? You want to overcome the amount of this. You want to minimize this distance move, so that the item can be nearer. Okay, so what I mean is, let's say you have this item over here, you bring it up. Okay, you bring it up over here. So you want it to be as near as the chop as possible, right? So when you start to chop, it may take 0.5 second, 0.5 second, 0.5 second. Instead of just now 1 second. Just now it's 1 second, 1 second, 1 second, 1 second. So the amount of distance move, if you minimize the distance move for this chop, you can eventually chop faster, right? I think you get what I mean. So therefore, we have to to find an amount of x such that we can achieve our desired chopping time, okay, efficient time. But what is the problem? Okay, if your let's say your item if your distance is too near, if it's too near, and it start to when it start to oscillate, you're like right. So this thing, if you were to go so near that it's just maybe 0.01 millimeter away, you put chop, 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 right? So eventually this thing will reach the forcing function, okay, will eventually reach the same resonance as the natural frequency. Okay, so we don't want it to happen because the force the the frequency of the force itself, let's say it's like that, and then the forcing function is also the same. So when resonance happens when you have the same amplitude, okay, same amplitude. In this case, our amplitude I don't know whether is it x. So hold on a while. Far it shouldn't be x, but it should be some amplitude. So when they are about the same amplitude, they will actually increase. So this one will add up to this one. So resonance happens when A and B are the same. So it will be A plus B. If they meet their resonance level, they will be like this. So eventually it will actually be very. So I will believe this will be amount of this is it signifies somewhat the amount of forces um that will cause damages to the spring and the damper itself. So you eventually cause more damages. Okay, so you want a optimum distance between the chop and your item, such that you will not damage the damping system much, because if you want to design this, you want a good damper, it actually requires a lot of time and effort to actually design it. So this is why this is it. I've talked so much. I hope you understand the force variation, how it is being applied in real life, although it's not a very good example. And so the key concept here is actually force variation is eventually it will it will, it will the steady state itself is when it is moving. When it is moving at a constant I would say velocity. Okay, constant velocity. Okay. So comparatively, the steady state for free vibration or free free vibration is when it is zero, because eventually it will dies down to zero. So the final value theorem is zero for damp free and free, while the final value theorem for force vibration may be some value. And then another key concept is that you require certain time in order to let it achieve its steady state. Okay, because you eventually you want to overcome certain momentum differences. So with these, I think I can leave you with this, and next video we'll talk about how to derive an equation to actually predict the resonance, because our main key purpose is to avoid the resonance. As I say earlier, you want the distance between them to be as near as possible while preventing any resonance to happen. So next video we'll derive an equation so that we can actually see how to solve this thing. So I'll see you in the next video.